In this section, we'll look at one-sided limits. So basically, the idea of one-sided limits is if you've got a function of some sort, and let's say there's a hole there, then it's possible that the limit from on one side is different than the limit on the other. And the picture I've drawn here, they're both going to be the same, but they could be different. So say, for example, we had a function like this. Then the limit on the left looks like it's one value, and the limit on the right looks like it's a different value. And so then what we would say is that the limit doesn't exist. Okay, so here, let's say that this number is 1, and then down here is -1, and this is some function f. We would say that the limit as x approaches 0 of f does not exist because the limit from the left of this function is, sorry, it shouldn't be 0 here, it should be, as we approach 1, 1 from the left, so say this is 1 right here, then the y value looks like it's -1, but if we come from the other side, it looks like it's 1. So these two numbers are not the same, and if they're not the same, then the overall limit fails to exist. So this, what goes right here, if these two numbers are the same, then that same number would be the limit sort of from both sides simultaneously. But if these two guys disagree, then this thing is just D and E, and there's nothing you can say about it. Okay, so let's look at a function that we won't look at graphically. So let's say that we have a function f of x is, and it'll be a piecewise function, x squared minus 4x plus 3 if x is less than 9. And then if x is bigger than 9, it'll be defined to be minus x squared plus 4x plus 93. Okay, and so our question is, what is the limit as x approaches 9 of this function? Okay, so to do this, we actually need to split this into two questions. Let's first compute the limit from the left, and then separately we'll compute the limit from the right. Now, the limit on the left, if you're approaching 9 from the left, that means that the x's are smaller than 9, and so the first line of the function is in control. So that's the one that we'll use. Okay. The first line of the function was the one that was applicable for x less than 9. And now once we've got just a polynomial here, you can just plug in as usual. So you'd get, what, 81 minus 36 plus 3, and that works out to 48. Okay. So all you have to do is substitute in which piece of the function you're actually dealing with here, and then once you've got that substituted in, you're just dealing with the polynomial. You can just plug in. There's no problem. Okay, now what about on the other side? If we come at this on the right, if we come at this from the right, then the other line of the function will be in control. And so this will be limit as x goes to a 9 from the right of minus x squared plus 4x plus 93. And again, we now have it down to the step of being a polynomial, so we can just substitute the 9 in and crunch it. And so we get negative 81 plus 36 plus 93. And this happens to also work out to be 48. Okay, so since these two numbers were the same, our conclusion is going to be the following. So therefore, limit as x goes to 9 of this function is the common value, 48. Okay, so then this number here is the common value of these other two things. Now let's say that one of these had come out to be different from the other. Then we would have said that the overall limit would not exist. Okay, so that's sort of the start for today. There's just one problem of pre-class. It should be really easy. And we'll kind of look at a little bit more what's going on with this in class and then formally define continuity.